Eigenvalue statistics for random relationships.
Hi, thanks very much, and thanks again to the organizers for putting together a really stimulating conference with a lot of different ideas being discussed amongst participants. And I also appreciate the opportunity to talk about some joint work with M. Krishna from Chennai. So I'm going to give a little bit of an overview and then mention some recent results that we got on local eigenvalue statistics. And I'm only going to be concerned about random Schrodinger operators. And I'll put down the models that we want to treat, the standard ones. So if I use this, I'll say RSO. And I'm also going to talk about both random Schrodinger operators of Anderson type on the lattice, so in ZD, and also in the continuum on RD. And I'll go back and forth. I'll try to leave the basic model written over here so I can refer to it. So on L2 of RD, and primarily we're interested in cases where D is bigger than or equal to 2, so multidimensional cases. The Hamiltonian is always going to be the random family H omega that looks like a deterministic kinetic energy term plus a random potential V omega. And more or less V omega will be what we've seen before at this workshop. It'll be of random type. The Laplacian, depending upon the model, might change a little bit, as I will mention. So in the continuous situation, V omega of x is the Anderson type, so I take omega j, the random variables. I take a bump function, u, let's say it's positive compact support, centered at the origin. You shift it and center it at the lattice point j, so the j here will belong to points zd in the larger space, which I'll refer to as the continuum model, RD. In this talk, I'm interested in the most regular case. I'll assume these are independent, identically distributed with a density. The probability measure has a nice density, bounded and compact support. Okay, that enters into some of the constants. Of course, you can generalize that, and this will just be a standard bump function, let's say compactly supported and non-negative, okay, for this case. So that's one situation that I'll be dealing with. So that's the continuum model. The other one on lattice, of course, the Hilbert space is either going to be L2 of ZD. Again, I'm going to concentrate on D bigger than or equal to 2. Or, as you'll see hopefully in a few moments, it'll be on a tensor product, L2 of ZD, tensor with some finite dimensional space. And the dimension of that space I'm going to call MK for some reason which I no longer remember why we call it MK. So it's either going to be a standard Anderson model here or a slightly different model on this space, depending. And for example, in the beginning of this talk, I'm going to refer to V omega at the site n is simply going to be multiply again by the random variable omega n times the projection Pn. And here Pn, to use a Dirac notation, is just the rank 1 projection on the site n. And this, calling it rank 1, as we heard even in Molchanov's talk just a moment ago, is going to be important. And this other model, these projections are going to turn out not to be of rank 1, and that will be one of the types of models that we want to investigate. So the other goal which I'd like to have in talking about local eigenvalue statistics is to separate out the role of 3 different methods that are used, at least presently, for Schrodinger operators. That is to say, the so-called Wegener estimate, the Minami estimate, and localization, and try to see and show you where each of those 3 estimates enters into the calculation of the local eigenvalue statistics for these models. So let me begin with some very general results. And as always in dealing with these models on infinite volume spaces, we first take the Hamiltonian and restrict to bounded domains, which I'll just refer to as lambda, which will be bounded domains in either RD or in ZD. Occasionally, I will write lambda sub L if I want to write down explicitly the length scale. I might do that later on. So these are nice bounded domains. So I don't want to just take the nicest thing, take cubes, working in CD if we want to. Then we take our Hamiltonian h omega, and I actually want to put this omega upstairs rather than downstairs. Sorry about that. So I take h omega, I restrict it to this domain plus some sort of self-adjoint boundary conditions on the boundary of lambda. So let's say Dirichlet boundary conditions, and then I will call that local Hamiltonian h omega sub lambda. Okay, and so of course what this has done is that it's taken any of the essential spectrum and gotten rid of the essential spectrum so that we just have a discrete spectrum for these models, and I will call those E sub j super omega of lambda. So those are the eigenvalues of h omega sub lambda. So that's the those are the objects that we want to study their behavior of. The other thing, just point out, of course, in the continuum model, there are infinitely many such eigenvalues. In the lattice model, the number is the number of points in lambda. Okay, so you have a finite number. That doesn't really play a role. Now, let me write the first basic estimate over here that is true for all of these models, the so-called Wegener estimate, which we've heard about in other talks. So the Wegener estimate says what's the probability that this Hamiltonian has at least one eigenvalue in some energy interval. Okay, it's one of the fundamental estimates that we have to work with. Occasionally just refer to it as W in square brackets. So the probability that h omega lambda has bigger than or equal to one eigenvalue in some energy interval I. So I is subset of R, some bounded interval. And that, as we've seen before, is bounded by the length of the interval times the volume of the region to which h is restricted. So I'll put some constant times the length of I times the volume. So it's linear in the volume and the energy interval. And so what can you say? What's that? Did I do probability that this thing has at least one eigenvalue, right? Is bounded, oh, this is W, not omega. That's W for Wegener, right? Right, sorry. Does not depend on omega. You know, how about C0? What's that?
For sign definite.
For sign definite, right. Yeah, I mean, so that's the only case that I was, I mean, no, well, okay, there are other extensions, but that's not really what I want to talk about. So what are the local, what's the basic object then for the local eigenvalue statistics? And then I'll also write over here, so LES. So let's pick an energy E0, and the E0 is going to be the reference energy. That's why I'm talking about local eigenvalue statistics, local with respect to E0, and that's always going to be chosen to belong to sigma, which is equal to the spectrum of the infinite volume Hamiltonian almost surely, as we heard about in some other talks. Okay, so I'm just going to pick an energy that's in there. I'm going to look at how these eigenvalues behave nearby that E0. So from this Wegener estimate, the mean spacing of the eigenvalues is approximately 1 over the volume. So we're going to scale the difference between the EJs and the E0 by the volume. So basically, we're going to look at the finite point measure, random point measure, and I'm going to give it a name, psi omega sub lambda, and I'll write it as a measure on the real line, which is just a sum of Dirac delta functions at the appropriately rescaled eigenvalues. So it's just a sum as j goes from 1 either to the volume lambda or to infinity of the Dirac delta function. So it's the rescaling, because the average spacing is, by this estimate, 1 over lambda times ej omega of lambda centered at E0. Okay, S is my parameter just to make that a measure. So that's corresponds to just a bunch of points distributed that way on the line. So I'll often go back and forth between these point measures and point processes in the talk. They're equivalent here. And so we want to know what happens when lambda goes to infinity. Okay, so that's the first first thing that we want to learn something about. So let me just write down, so here's the goal, first goal maybe, is to study this family as the volume goes to infinity. All right, and of course that's been studied by many people, and I'll try to cite some authors relevant to what I'm talking about here. So the first thing is a rather simple consequence. Folk theorem maybe, it's written down at least in some papers by Nakano, which I'll mention. So for any E0 in deterministic spectrum, in fact any E0, this family psi, omega, lambda has weak limit points, and I'll always refer to those. So you always can find weak limit points of that family, and the proof of that just comes from the Wegener estimate. So I'll refer to them as psi super omega. So there may be many of them. There might be one of them. That's actually, in general, one of the questions we'd like to answer. So it has weak limit points that are point processes. I don't know if this is a theorem, just an observation, that are random point processes. And so this is just basically a compactness result, and I can show you quite quickly what that relies on, and it only uses the Wegener estimate. So the first few things I'm going to mention just use the Wegener estimate, and then we're going to refine by, in some sense, getting information about more moments. We're going to refine those results. So the proof of this is just a tightness bound. And so what you need to show is, for example, you take the lim sup as the volume, in this case, goes to infinity, of the probability that this family, psi omega lambda, for some interval I, so basically you're taking the number of points, rescaled points that fall in the interval I, the probability that that's greater than t, you have to, of course, prove that that's equal to 0 in the limit that t goes to infinity. Okay, so this condition would guarantee the existence of these weak limit point processes for these finite volume family that I introduced. And of course, you just use the condition W, the Wegener estimate, because you know that the probability that, in fact, these variables, these random variables in lambda are bigger than or equal to t. Well, by Chebyshev, that's 1 over t times the expectation. And this expectation can be rewritten as a trace, right? That's the trace of a spectral projector in this rescaled interval for the Hamiltonian, and that's estimated the same proof. Even though I wrote this in probability, you can also write that the expectation of the trace of the spectral projector for the Hamiltonian h omega lambda in the interval I, the expectation of this trace has the same, enjoys the same bound. Right, the length of the interval times the volume. In fact, that's what you prove. You prove the upper bound on the expectation. By Chebyshev, that's an upper bound on the probability. So that's the way it goes. So this, of course, is then simply less than or equal to 1 over t. Now, if you carry out the rescaling, so remember in the definition of psi omega lambda is a rescaling by the volume, that gives you a 1 over the volume times the length of the interval, and then, of course, times the volume to which the system is constrained. So the volumes drop out, right? That's where this rescaling is helping us. So the volumes exactly drop out, so you can verify immediately this condition. So already we know that there are at least weak limit points of these point processes associated with the eigenvalues in a box, and of course, what we want to do then, so maybe goal number 2, so having established that, is to figure out what they are. All right, so goal now is to characterize the weak limit points. The weak limit points, and of course we need more information. let me state what might be considered folk belief for random Schrodinger operators, at least in dimensions 3 or higher, about what should happen, some of which has been proven and a lot of which has been not. So I'll put it as a belief or conjecture, I don't know, whichever we'd like to subscribe to. And let me, to eliminate disbelievers, let me at least say dimension 3 or higher. Okay, so that that's it's open. So now we know that this deterministic spectrum of the infinite volume family, right, almost surely, it of course admits, you can look at the spectrum of anything, any self-adjoint H omega, you decompose it into its 3 components, it's AC, absolutely continuous, singular continuous, and pure point. It's been shown many years ago that the same thing is true for the deterministic spectrum for this family. So you have pure point, singular continuous, absolutely continuous. Those are not actually going to concern me here. What I want to do, though, is I want to consider a subset of sigma, which I will call the region of complete localization, which Alex and Abel were talking about a few days ago. That is to say, the region where everything which you would like to have happen happens concerning the localization, pure point spectrum, exponential decay of eigenfunctions, uniform localization, such for those models. So the first statement that I'll make under the belief is that if you take our reference energy in this region of complete localization, well, this has been studied a bit, then that implies that, in fact, there's only one limit point, as I'll mention more in a moment, and in fact, this is a Poisson point process. I'll say more about that in a few minutes, right? So that's what the belief is in the localization regime. Okay, so of course, what one is wondering is what about the rest of the spectrum? So here you're considering disorder is fixed, right? So that there is something outside of the complete localization region. Well, that's of course an interesting and completely open question. And some think that it should be the same as GOE. So there's some belief that this should be the sign 1 distribution, the sign 1 process. So one goal might be to get some incremental growth in that direction. And I'll just mention some incremental things later on. So that would be some connection with random matrix theory, if indeed one could establish that in this general setting. Okay, so that's why I just say that's a belief. Now, in order to exploit more about the structure of these random Schrodinger operators I'm describing, we want to introduce more machinery. So, yeah. Because even the theoretical physicists don't have a strong, well, individuals do, but I don't think there's a community belief about whether there should be something outside of the complete localization regime in dimension 2.
Also in the complete localization, you would expect the Poisson.
Oh, sure. Yeah.
Okay.
Right. So I just wanted, right. In dimension 1, you have localization, as we've heard, at all energies. You have Poisson point process, right, for this standard model, right, that we're doing. So, but I wanted, I mean, in some sense, this would be, of course, the 2-dimensional case is extremely interesting. If you say anything, that would be great, a weak disorder. But in some sense, this maybe is the least ambiguous or the clearest statement you could make as a possible conjecture, right, what happens in those dimensions.
May I ask a very simple question?
Oh, yeah, well.
Is it known that this set of complete localization is almost sure the same?
Almost what? Sorry.
Almost sure the same.
Mm-hmm. The same in what?
Doesn't depend on omega.
Doesn't depend on
Yeah, complete localization. With probability 1, the same thing.
Oh, is it independent of omega? Yeah, sure. It's almost. This is known to be almost surely independent for these models, right? Right, and that goes from work of Germanet and Klein, and maybe even back before that. Right, but the characterization, right? Okay, so that maybe be something that is guiding some investigation here, let me sort of pause to introduce what I would sort of call now a tool to help investigate some of these questions. And I hope to make it clear why I'm calling it a tool at the moment, and it's not really, it could be a hindrance also. So let's suppose that you take the region lambda, you've seen, and divide it up into subregions, right? So on each subregion, I'm just going to write them lambda sub little l. And of course, this is my big region, lambda sub big L. For example, you can take little l to be a fractional power of big L. So I'm going to take the Hamiltonians with Dirichlet boundary conditions on each of these smaller pieces. And of course, the eigenvalues associated with those Hamiltonians are independent because the random variables in each box are independent of the random variables in the other box. So this way, by taking this decomposition over lambda sub little l p, so p is going to go from 1 up to capital N sub l. N sub l, of course, is nothing more than large L divided by little l to the power d. Just write it that way. So you have this decomposition, and similarly, with each region, you make a Hamiltonian, which I'll now write h omega sub little l p. P goes from 1 up to N sub l, right? And what I'm going to do is I'm going to construct an array of independent point measures. And there's a big theory on the convergence of array of independent point measures, right? So divide this up, and let me introduce those independent point measures for each such Hamiltonian. And I hope my notation will be consistent here. So I'm going to introduce these LP of S again. So these are going to be the sum over. I'm going to scale with the same large volume. So even though I'm looking at the eigenvalues of the Hamiltonian on a smaller box, scaling, I'm going to keep the scaling of big L to the d times the eigenvalue, so E sub omega, and now I'll have to give these guys a name, J of lambda little l p. P goes from 1 up to N sub L. So at our centered energy E0, as if you write it as a measure. So I have a family. I have N sub capital L of these point measures for each decomposition for each L. And then, of course, I want to sum these up. So I'm going to sum P goes from 1 up to N sub L of eta omega L P. And I'm going to call the sum zeta super omega sub capital L. Okay? So I've constructed an array of independent point measures, and then we can ask about the convergence of that. Okay? It turns out that Wegener, if you look up in the book about these arrays, allows you to show that this collection is a, always get the word ordering right, is a uniformly asymptotically negligible, I can't even spell that word either, negligible, negligible array of point processes. And so there are some conditions one needs in order to verify convergence of that, which I'll do. So you can prove this asymptotic negligibility, and of course you know that this family, by the same reasoning, so this family has weak limit points that are also point processes. We've gained one thing. The limit points are also infinitely divisible because of the construction using this asymptotically negligible array. So the limit points have, what's that?
What do you mean by uniformly asymptotic? Is there something else that goes to infinity now? Are you sending NL?
I'm sending, so I have for each L, I have N sub L of these things, right, index by P. So that forms an array. It's a triangular array,
yeah,
right? And when I send cap L to infinity, that array, well, you can prove the same tightness bounds. You can prove that it's actually asymptotically vanishing. That's what asymptotic negligibility means. And so that the limit points exist and they're infinitely divisible point processes.
Because my question was, what goes to infinity here? So you said
L.
L goes to
L.
infinity, and
Yeah.
little l.
I said it, and I'm sorry, maybe I should have written it. Little l is a power of for alpha less than 1, bigger than 0. Right, so this array is getting
Yeah,
bigger.
so that makes
right?
sense.
Yeah. Sorry if I should have written that down, had that in my notes. Okay, so these have weak limit points, and if I take any one of them, psi omega is an infinitely divisible point process by construction using this array. Okay, so any model, any situation, you can always do that. You always get these family of limit points that are infinitely divisible. Okay, so that's a tool that we'll use. The next
Sorry. So the ingredients of the sum are negligible.
What's that?
What exactly? Can you please say again? What is negligible?
This array, right? So there's a technical condition which I can write down that is quite similar to the tightness bound, right? In the tightness bound, yes, the probability that something is big, that it vanishes when you take a look. So it's quite similar to that.
Probability
So that gives you the array.
to this small interval, finite interval I, is very small.
That's exactly what I
Yeah, it's rescaled. So
understand.
my rescaling of the eigenvalues means that I'm looking at 1 over the volume times the interval I plus E0 is another change of variables. Yeah, okay.
So,
So I haven't done anything except written down some definition.
sorry, this is very interesting. So do you have one example of something that is an infinitely divisible point process that's not Poisson that could come up here?
Yeah, we'll see a generalization in a moment, right? And then we'll also see something where it probably is not infinitely divisible. I mean,
Main obstacle here is that it can be compound partial.
sine 1 is not infinitely divisible.
Compound partial when there is multiplicity.
Okay.
We'll hopefully see that within 10 minutes. And sine 1 is not infinitely divisible. So in that regime, it shouldn't be infinitely divisible, right? So, but I haven't done anything. I just wrote down, you can always do this, okay, for any model. You always get these guys. So now the next ingredient, so I started with Wegener, the next ingredient is localization. So what does localization buy us? Okay, and that's where this tool will be used. So let me go just mention then how we improve things by adding, by effectively taking E naught to be in sigma CL, which is the next step. Let me go to that. So okay, so this is the second part, as I said, after Wegener. So if you simply take E0 in this regime of complete localization for these models, then it is not difficult. It's well, it's a couple of pages, but it's a rather standard calculation. I'll give a starting point in a moment to show that these weak limit points are the same as the weak limit points that are obtained from the Hamiltonian on the large box. So localization is used to prove that the weak limit points of the process for the Hamiltonian on the big box are the same as that gotten by this construction using this asymptotically negligible array. That's where localization comes into the game. And of course, what it's saying from the point of view of decay of eigenfunctions is that the effect of the boundary conditions here, right, between the Hamiltonian, that's a direct sum of the Hamiltonian on each of these boxes, lambda sub little lp, and the Hamiltonian on the big box, those boundary conditions wash out when you take the volume to infinity. Okay, that they're negligible in terms of you just think of the difference of the two resolvents and doing some Green's function estimate, that boundary term disappears as the volume goes to infinity, and that basically is how Minami proved it back in 1996. Okay, so if E naught is in the region of complete localization, then these processes this and zeta omega lambda have the same weak limit points. So in particular, any psi omega is also infinitely divisible point process. So perhaps this is clarifying a little bit the situation that with Wegener, you know there are limit points, you know there are point processes for the infinite volume situation. If you add that the energy you're localizing about is in the region of complete localization, then you know that these are infinitely divisible point processes. That's all this. Maybe it buys you more, but at the moment that's all that I know that it buys you up to this point. And so the proof of this by many people, so Minami, Germanet, Combe, Germanet, Klein, sorry about that. And there are a couple of papers by Nakano who do this sort of decomposition. I should also add the paper of Germanet and Klopp here. And basically what you do is you look at the expectation of the Laplace transform. So I'll just write down one formula. So if you look at the expectation of the Laplace transform, e to the minus x of, let's say, two non-negative random variables, e to the minus y, take the absolute value, bound that above by the expectation of x minus y. Okay, so you have this upper bound. And so for x and for y, you simply take these local point processes and you test them with some test function. And so what you have to estimate then to do the proof is you have to end up the expectation of, let's say, psi omega lambda of f minus zeta omega lambda of f for suitable test functions f. And then again, you implement the idea by using the resolvent, using the localization decay of the Green's function from the center out to the boundary, that in fact, when you write this out using, let's say, functional calculus due to Helfer and Soustran, that in fact this goes to 0 when the volume goes to infinity. Okay, so that's the key ingredient for that amount. So that's one situation then that you get. So we learned one new thing, that you have infinitely divisible point processes. Okay, and I'll just mention finally, if you take, of course, E0 belonging to the complementary set, so the other energies in sigma, then in fact we don't know anything else at the moment, right? Psi omega, one of the limit points, is simply just some point process. All right, that's at this stage. So that seems to be up to here, what we get out of this. So the Wegener estimate, one can think about, especially when you write it as, right, it's an expectation, the first moment of this random variable, the trace of the spectral projector. So you'd like to go up and look at variance, so look at second moments. Well, in this game, that's called the famous Minami estimate. So the last step of these three steps is, what is the Minami estimate and what does it buy you in this situation? Okay, and how does it improve our understanding here working towards this belief? So let me briefly recall and write down what the Minami estimate is and then improve things a bit more. So there are a couple of ways. Well, there are two main ways to write down the Minami estimate, a strong way and a weaker way. Let me first, let's see, I think I first want to write down a weaker version of the Minami estimate. Yeah, so let me put this over here, call it M, so I can leave it on the board. So basically, you want to know about probability that you have two or more eigenvalues in an interval, right? And so that's the essence of Minami. So one way to write it is to look at the sum as j goes from 2 to infinity of the probability that the local Hamiltonian, h omega lambda, has at least j eigenvalues in the interval I. Okay, so this is the type of estimate that I'm going to be talking about for the moment. And that's bounded above, again, by a constant. They call it C1. And now it's like the square of the Wegener estimate, if somehow you could decompose, if you had independent, if those random variables of the trace, as I'll show in a few moments, that's like the expectation of this random variable, the trace of the spectral projector times itself. So if they were independent, you take the square, and that's the upper bound that you would get. Okay, so what do we know now if we add the Minami estimate? And that's pretty much consequences of Minami estimate, pretty much where we are at the moment. And here, let me just say, this is the first place we have to distinguish between lattice models and continuum models, right? So let me look at lattice models first. And so I had written on the left-hand board there that the lattice model in this particular setting, the first one I wrote down, the projector here was rank 1. And so what I'm going to write now is for the rank 1, so Pn is rank 1. Okay, and for this situation, then in fact, the Minami estimate holds. It was proven originally by Minami in all dimensions in his original paper. And then we have the following. So what do we know? For any, there's three things to write down. So for any E0 in the deterministic spectrum, take a look at zeta omega. So what is zeta omega? That's the infinitely divisible point process that we got from the array. So it started any energy that's always Poisson distributed, right? So it tells us something when we add localization, but it doesn't tell us much outside of the localization region, right? So this one is always a Poisson point process. And to be more precise, the intensity of the process, people know, is given by the density of states for the problem at the energy E0. Okay? So that doesn't tell us a lot. This is the one that was constructed from an array. And because it was constructed from an array, it always turns out to be Poisson distributed. Right? It doesn't really see the localization. The localization is used then if I take E0 in sigma CL. Then in fact, we know that this one that comes from the local Hamiltonian, this has the same limit points as this one, right? So let me just say those have the same limit points. And so that implies in this case, the local eigenvalue statistics is also Poisson. Okay? And then with reference to a comment I made a little bit earlier, if you take any other energy to center the LES, so if you look here and you look at the complement, well, what do we know? We only know that we have these point processes, and we're probably certain, although no proof to my knowledge yet exists, that it's not an infinitely divisible point process. So it's probably not, most indication, infinitely divisible. It would sort of be nice to have a proof even of that, because of course we don't know very much about the behavior of the system for energies outside of the complete localization regime. So that's the general situation. I just wanted to mention, of course, actually I want to save that for the continuum. So that's the lattice. So again, here, well, big question marks, don't know what's going on in that situation. And then let me just say the continuum models, as I've written on the left. Where are we with those? So at this stage, so we're here on continuum. So on L2 of RD. Okay, so again, if you take E0 belonging to sigma, then the ones constructed from the array, this again, all we know now is that it's an infinitely divisible point process. And that's what we got just by its construction for the array. I should say probably right offhand is that we have no m. All right, and so that's the problem. We have no, this estimate as I wrote over here, m, in higher dimensions, in dimension 1, I'll say a comment in a moment, we don't have this. Right, and so we can't get anything else. We can only get this result. But this is the one, this just sort of followed by definition from the array. And of course, if you take E0 in complete localization, we only have this fact that the zetas are still, of course, if you're still in localization regime, these guys still have the same weak limit points. Okay, so it's infinitely divisible, but alas, we still don't know if it's Poisson. Right, that's open. But we'll say something in just a few minutes about that. So Molchanov was the first one, I believe, to work on some one-dimensional models on the real line. Frederick Klopp worked on the real line, and Christopher Shirley worked on some sort of similar on some lattice models quite recently. So that's some previous work there. Okay, now to talk about some additional ideas here. There were two things that had bothered and continue to bother a lot of people. And let me finish up by saying what those two things are and how it fits into this overall scheme of wandering erasers. So what about this Minami estimate? Okay, this has been a problem for the people working in random Schrodinger operators in the Hilbert space L2 of RD for a long time. And so some things, and also on the lattice, and now I'm going to refer to this model down here, which I'll mention more in just a moment. So let's go and talk about first lattice models. Extended Minami. So an extended Minami estimate. So this is sort of a warm-up. So suppose either you take some models of the type that at every site you put some projector that has a uniform uniform finite rank. Okay? Or you talk about so-called polymer models. Okay, so instead of taking on ZD a rank 1 projection, you take a box in ZD and you associate one random variable with that box and you tile the whole ZD with that fixed size. And that would be the rank of that, the number of points in that would be my MK. Okay, so we want to look at basically at Laplacian plus, so H omega is Laplacian plus a sum over J in some index set, say script J, of omega J, Pj, where the rank of Pj is uniform, and it's going to be Mk. And you want something so that if I take the range of the Pj's, and if I take the union over all J in that index set, so I'm thinking of the polymer models, in that case you get all of ZD, right? So you're just covering the space, right? So a dimer model on Z, right, on the integer line, for example, would be every 2 sites you have one random variable. So you have 2 with the same size, next to the same size, next to the same size. So there the rank would be 2, uniformly 2. So the usual form of M that people prove is not exactly the form I wrote over there, but it's the following. If you let X be equal to this trace, this random variable of h omega L of an interval I, so let me call it x sub L, then usually what one estimates, it's very easy to show that the sum of the probabilities on the right-hand board can be bounded above by the expectation of xl times xl minus 1. And so usually one tries to attack that second moment of that random variable xl, and that can be shown in this lattice case when the rank 1 projector, this is bounded by Cm, the same thing, the length times the volume squared. Okay, and this is for rank 1, when the PJs are rank 1. So what happens in this case? Let's say the polymer models where the rank is mk. Well, it turns out you can extend this Minami estimate by replacing that 1 by mk, the rank of the projectors. So the extended Minami estimate is not very difficult to prove, given the framework by Combe, Germanet, and Klein. The extended Minami estimate is basically that the expectation of the random variable xl times xl minus 1 is, xl minus mk, sorry about that, mk. Well, this, of course, need not be a positive random variable, so let me just restrict that to a set where the random variable xl is bigger than or equal to mk, so it's positive, is bounded above by the same thing, some other constant c2 times the volume times the interval squared. And actually,
Is
yeah.
Is mk, is that something that depends as a function of k, or is that just some fixed number?
As I was trying to say earlier, somehow, for a reason I've long forgotten, it's just a fixed number. It's a fixed positive integer. Right. And I don't know, I should change it to something else, but since I was trying to distinguish it from other indices. Okay, so now you can get somewhere for these models. So you don't have ordinary Poisson. So even if Minami, so even if you're in the localization regime for these higher rank models, you don't know what you're going to get. But it turns out that you can get something in this situation. So here is a theorem about higher rank lattice models. Higher rank lattice. Okay, from this extended. So if you take psi omega be any limit point, and if, of course, E0, now I'm going to use localization, use Wegener. I'm going to indicate that now if we use this extended Minami estimate, we can actually say what the process psi omega is, or any of these limit points. We know it's infinitely divisible because we're in the localization regime. So we know that it's the same as the one coming from the independent array. Okay, so we can't quite, because technically we can't prove that any of these limit points have independent increments. So we can't quite prove that yet. But what I can do is take any interval in R and look at the random variables associated with one of those infinitely divisible point processes, right? So this is a random variable. Well, it turns out that this Minami tells you that, allows you to prove that this is distributed according to a compound Poisson process. Okay, so that's the first result. So this random variable is distributed according to a compound, which is a bit more technical or more elaborate Poisson process. And let me just write down a formula which is very informative. That is, if I look at the characteristic function of this random variable, right, so the expectation of the exponential of that random variable, then this has a very beautiful form which identifies it as being distributed according to a compound Poisson process. It's a sum as j goes from 1 up to mk of e to the I jt minus 1 times some numbers pj of I. So if one's familiar with Lévy processes, or of which compound Poisson processes are an example, this is saying that the Lévy measure for this process is supported in the set of positive integers 1 to the rank of the projector, And in fact, the weights are given by these p sub j of the interval I. And there's a formula for each of these. So the pj's of I are obtained by taking a limit along a subsequence, so as L sub k goes to infinity, of the sum as p goes from 1 to n sub L sub k of the probability that these random variables eta L p at I is equal to j. So you take the limit, remember the limit points of this are the same as the ones with the array, so if you take the sum for all the components that make up the array at level capital L, you sum those up, sum up the probabilities that each one of these, that is, there are exactly j eigenvalues in the interval I for the smaller Hamiltonians. That limit is the definition of that weight. This limit always exists at least along subsequences going to infinity. And in fact, the first one you can compute, because if the process were actually Poisson, you would expect, and it has to be, that P1 is non-zero, all the other ones are 0. So what we do not know is if we know that one of these has to be non-zero. I'll show you that in a moment, but we don't know which one is non-zero for these processes. But at least this gives a pretty good description of the Levy measure. So the Minami, the extended Minami estimate, is used to characterize the Levy measure. Okay? And so the one P1 is exactly what those who work in this would guess. It's given by the density of states at the energy E0 times the length of the interval I. Actually, that was a lie. That's not what I meant to say. At least one pj of I is not equal to 0, because if you sum all these j pj of I, if you sum over all those, then that's equal to the density of states times the length I, just by following through this definition and the equivalence between the processes. Again, if you're in the rank 1 case, this is exactly what you get, and it's Poisson. P1 is non-zero, it's equal to the intensity of the Poisson process, all the other ones are 0. Of course, you can make toy models, in particular on this tensor product space, you can make toy models where the eigenvalues have high multiplicity mk, for which P1 is 0, and for example, one of the other PJs is not 0, which means that the process is not Poissonian, and it's clearly more complicated. It's a compound Poissonian. But whether you have real random Schrodinger operators of the type I described is unknown. But there does seem to be a link I'll mention between the multiplicity of the eigenvalues and the process that you get. In particular, this extended Minami estimate can also be shown using the Klein-Molchanov method to say that the multiplicity of the eigenvalues in the localization regime can't be any more than m sub k. So it puts a uniform limit on the multiplicity. So in the last minute, let me mention, so these are the most complete results are for these dimer polymer models in higher dimensions, for these models in which you have a potential, random potential, which is matrix valued. So in the tensor product space, maybe a bit more interesting because of the lack of many results is that it actually says something about the continuum model. And so let me finish saying there my talk with that. So for the continuum model, of course, there's no Minami, as I said earlier. So what we did know, however, is that you can get these point processes. We do know that these exist, so these are limit points of psi omega sub L. So let's take an energy again in the localization regime, sigma CL. Then what you can say is the following. Indeed, for any interval I in the real numbers, then the random variable is also distributed according to a compound Poisson process. So that's a bit more information. It's infinitely divisible. Its characteristic function has a similar, not exactly, as I'll see. So this random variable is distributed according to a compound Poisson process. What about the Minami estimate? Where is that needed? Well, the Minami estimate allowed us in the higher rank lattice models to characterize the support of the Livy measure that occurs there in the characteristic function for the process. So here you still have a Livy measure. The only thing you can say is that it's supported on the positive integers. So the extended Minami estimate allowed us to make a bit more precise where the Livy measure can live based upon the rank of the projections that are in the random potential here. So the Livy measure is supported on n. Okay. Again, the weights are the same. The pj of i's are constructed exactly the same way. We know that at least one of them can't be 0 for exactly the same way that we do the construction, but we don't know anything else in this generality. So there are still a lot of questions. Remember, I put a belief and or conjecture to try to see where we might be going with local eigenvalue statistics, considering the localized regime, where now, even in the continuum model, we know something about the processes, okay? It's not a lot, but we know something about them. And in the non-localized regime, the rest of the spectrum, we know the processes are there, so a challenge is to develop some tools in order to study them. As I mentioned, there is a connection, it seems to us, between eigenvalue multiplicity and the process that you get. At least you see that in some of the toy models that we were able to construct. And it also, in some sense, we don't know in these situations whether there's a unique limit point or other characterization. So for example, as I mentioned a little bit earlier, finding that they have our processes with independent increments would help a lot. That seems to come down to getting a second moment estimate, just like Minami estimate, so maybe we can't do that. So getting an expectation of this random variable squared. We had some estimate on that we could prove independent increments. So you might say that's the same as a Minami estimate, so maybe we're just going around in a circle.
But at different i's, right?
What's it? Yeah, yes, at disjoint, at I and at j. Thank you, not the square. Well, you can use Cauchy-Schwarz and reduce it to the square, right? So if you have x for I, x of j, expectation, it's less than or equal to the expectation of the square plus the other one. But I actually don't know how to do that estimate yet. So that's something we're doing. So they're just, hopefully it gave you an overview of local eigenvalue statistics, at least how Christian and I see it right now, and thank you for your attention.
Thank you very much. Shouldn't the uniqueness of the limit point just be a consequence of the localization?
Well, I can't say no, and I can't say yes.
I mean,
I can't disagree, but I mean, we've thought about it.
The feeling is that when you, but the idea is the following: when you let L go to infinity, you increase the size of the box, right? But what the eigenvalues looks like just depends on local behavior around where the eigenvalue is sitting. That's the gist of localization, right? So it shouldn't feel this, right? It should not be able to move around.
Well, I mean,
I would think that actually localization. I mean, of course, if you just add vector, there's nothing you can say. But if you have localization in addition, you should be able to say that you only have one limit point.
I mean, that's encouraging. I mean, we're just we believe that, and then turn around.
I don't think Minami actually is.
No, Minami is not needed for that.
I don't think it has anything. It just has to do with the limit. With what does the limit process look like?
I agree. Right.
So I think that localization should be enough. If you look at the way in our paper with François, we used Minami because we wanted to get the full result. And but Minami doesn't come into when you cut things into pieces, right? It comes into some estimates.
Right.
But it seems to me that because the eigenvalues, right, just depends on the local structure. When you go to the limit, increase the box, nothing changes for the eigenvalues that are living inside.
I mean, I would agree with you. Just up until now, we hadn't come up with a proof of it. that it was actually unique. We talked to some other people in probability, we weren't so sure, but I agree with you, so we'll go back and work more. try to do it, right. Well, just like the independence too that we talked about, right? Still
Of course, it also depends. The fact that you have something which is stationary is important, right?
Yeah.
Because
Well,
you
it
could
is
have. I mean, you are creating eigenvalues elsewhere, right? If the things would be different
Oh, yeah,
elsewhere,
right.
because it's,
Yeah.
then presumably new things
Yeah.
would come up. But otherwise,
Peter, what I think Frederic is saying, there is this usual proof that you are using,
Right.
that you divide it, and if you can show that certain estimate to here usually come from Minami, then there is unique limit. I haven't seen theorems like that apply in the situation that you can have and
It seems like
then be proved. That was basically
Yeah.
what Frederic is saying. Can
Yeah.
be proved.
yeah.
It's a general statement in probability theory.
Somebody here knows, maybe. I
Right?
mean,
That would be a general statement in probability
well,
theory.
he's saying no, that we should be able to do it by
A
hand.
second moment or something, but something.
I don't
end
think there's.
moment.
I'm not sure there's any general theorem that will apply,
Yeah.
but using localization, we should.
exactly. I don't see how you translate
Tried a
direct
couple weeks
localization.
ago.
But the
Yeah.
localization is basically
But-
giving you the asymptotically negligible array.
Yeah, and
The
it
only
gives
place
us
the
a
vector.
localization
Yeah.
works. Now, there is a proof probability that if you have that, then you get.
Yeah,
what
you
you
have
want.
that, you have the first estimate, and you have Minami, then you get
Yeah.
uniqueness.
But
And
if you
uniqueness
replace
is part of the
them
proof.
by the more generalized one,
Right.
at least in probability literature, they have not worried about that.
Well, I haven't
Can
found
one
it,
prove
yeah.
that result?
Yeah.
That's I think what Frederic is saying.
Oh, yeah. Well, using localization bounds, right.
Gentlemen, I apologize.
Because
we
it
can-
just depends
I,
on what
I,
the
think,
country.
I think that this
Yeah, we can
has
go
a
on.
great potential of growing into a full-scale discussion, which
Right.
goes beyond the timetable of this session.
It cuts into lunchtime.
And lunchtime.
Right, right.
Yeah, so
Yeah.
thank you very much.
I appreciate it. Thanks.